Let's talk a little bit about orbital motion. So let's consider an object in motion around another object because of its gravity. Let's say like the moon in orbit around Earth. We could relate some variables, right? So we could ask, how do we relate, say, the orbital velocity? So there's v, maybe v orbit, to things like masses and radii, right? So we've got some orbital radius here. Let's call it r sub o. All right, how to relate those things? Well, we can write Newton's second law in the radial directions, or direction, right? So the net force, I can do better. The net force radially equals mass times some acceleration in the radial direction. Again, I just mean directly toward or directly away from Earth. In this case, the only force radially is gravitational, right? It's capital F capital G, right? And I guess if it's radially inward, we could call that negative. That's going to cause centripetal acceleration, which we would also write as some negative thing in the next line. So we'll do this. Minus Fg equals m times minus v squared over r. Okay, so here the minus signs kind of go away. They don't really matter because both of these are radially inward. And v is v orbit, and r is r orbit. All right, so I can relate the orbital speed and the orbital radius to the gravitational force, right? So gravitational force is g mass of the Earth times the mass of the Moon divided by the orbital radius squared equals mass of the Moon times v orbit squared, also divided by the orbital radius. Okay, so we see, as happens often, the mass of the orbiting thing goes away, and the mass of the orbiting thing goes away, and what we're left with is g, m, v, and the orbital radius. I want to point something out here, and that is that this combination of capital G and the mass of the Earth shows up anytime we have something attracted to the Earth. Isaac Newton never knew what capital G was because in his time they did not know the mass of the Earth. So in all of his expressions, he could not tease out G times m sub e. It was always one single constant. Since that time, we've been able to do experiments where we measure G between two lab scale objects. You have to do a very precise measurement of two massive things that are very close to each other. But you can get capital G out of that, and then you can get the mass of the Earth. There are other ways to get the mass of the Earth as well, but Isaac Newton never knew it. Okay, so we could solve for, say, the orbital velocity. So orbital velocity is going to be, we're going to multiply by an r orbit. That's going to give me gm over r, and then I need to square root it. So gm over r and a square root. Okay. So we need to be careful here. This mass is the mass of the thing being orbited and not the mass of the orbiting thing. Does that make sense? So when I'm calculating an orbital velocity, I need the mass of the thing I'm orbiting, right? So we could get, say, from information we know about the Earth, we could get the mass of the, if we knew the orbital velocity, we could get the mass of the Sun very easily. But again, the mass of the Earth cancels out from both sides of that, so we can't get the mass of the Earth from that information. The other thing to take note of here is downstairs, again, is an r. That r is not the radius of the planet, that is the radius of the orbit. And that's an easy thing to screw up, so Just be aware. The other thing I can do here is I can calculate an orbital period. I just want to remind you that velocity is distance over time. So if I knew a distance, and if this, we're going to treat this like it's circular. It's not circular, but it's close enough for our purposes. So the velocity is a circumference, which is 2 pi r, so that's orbital velocity, divided by the time it takes, which is a period, right? And so for the Earth, the period is a year. So we can turn that around and solve for the orbital period if we wanted, and we probably will. So I'm going to put a box around these two equations. These are useful to remember. Let's do an example. I would like to do example number 13. See if I can find that here. So an Earth satellite moves in circular orbit at a speed of 4.5 kilometers per second, right? 4,500 meters per second. What is its orbital period? Okay. Okay, so we can draw a picture. An Earth satellite. We don't necessarily mean a literal satellite, meaning like a satellite, a man-made satellite we put out there. Satellite in this sense just means something that orbits something else. That said, I'm going to draw it as an actual satellite because why not? Okay, so there's my circular orbit. Here's Earth. Okay, so we can label a couple of things. I'm solving for orbital period. I'm given an orbital speed. It's 4,500 meters per second. What is orbital period? So t equals. Okay. So let's talk about this. I have an equation, right, that v naught equals 2 pi r over t. I'm solving for t, so t equals 2 pi r over v naught. But I don't know r, right? I know the radius of the Earth, but I don't know the orbital radius. And those are two different things unless you have a very low orbit satellite, which we have an example of that later in this handout. But let's not assume that r naught is the r of the Earth. Okay, this is definitely not drawn to scale, but r naught's not the radius of the Earth. Okay. So what other equations do I have? Well, I have that g equals g m over r squared. But I cannot assume at r naught. What is that going to give me? I could maybe guess that I could use that to solve for r, right? And then go back and solve for the period. But again, I can't assume that g is 9.8 because that's only true when this r is the Earth radius, right? But if I'm further than the radius of the Earth, the lowercase g is smaller than that. It's not 0, but it does fall off. It does get smaller. Okay, great. So what else can I do? Well, I can do this one, right? That v naught is square root of g m over r naught. All right. Okay. So that'll let me solve for a radius, and then I can solve for the period of this motion. Okay. Okay, so let's do that first. Let's solve for the radius of this. So we'll use this first, and then we can use this to find period. Okay, so I'm just plugging in. 4,500 meters per second. Let's square both sides so I don't have to draw a radical sign again. 6.67 times 10 to the minus 11 times the mass. Okay, again, what is that the mass of? Is it the mass of the satellite? No, because A, we don't have that, but B, the derivation of this problem, of this equation, V naught equals, not V naught, VO, V orbit, equals the square root of GM over R. M is the mass of the thing being orbited, and R is the orbital radius. Alright, so I could put an R naught here just so I don't confuse myself. Okay, so that's 5.97 times 10 to the 24 kilograms divided by orbital radius, which is what we're solving for part 1 of this. Okay, so what I get for the orbital radius is 1.97 times 10 to the 7 meters. Okay, so to put that in perspective, the radius of the Earth is 6 times 10 to the 6. So this is not an order of magnitude larger, but it's quite a bit larger. All right, so this is very high orbit. I do believe this is higher than the moon, right? This is further out than the moon because the moon doesn't travel quite this fast. I think it's more like a kilometer per second. Okay, so now we can plug this guy in up here, well, here, to solve for V naught, or period. We're solving for period. Okay, so 2, let's do period equals 2 pi R naught over V naught. Again, it's not really a naught, it's an orbit, V orbit and R orbit. Plugging into that, 2 pi times 1.97 times 10 to the 7, that's in meters, divided by a velocity, which is 4,500 meters per second. That's going to give me a number in seconds, which is 27,500 seconds. You know what? I was wrong, actually. I had this backwards. It's high orbit, but it's not as far as the moon, because the further you go out, actually, the slower you need to go. I was wrong about that. So this is 27,000 seconds, which is about 7.6 hours. So I will say this must be closer than the International Space Station, because that orbits every, I think, 80 or 90 minutes. So this is further out than the space station, but not quite to the moon. Okay. Okay, that's great. Let's do something else. What else can we talk about for orbits? I am so glad you asked. Okay. So I could take these two equations that I have right here. I could plug one into the other. Right? Really, I could set them equal to each other, right? And you say, yeah, I mean, I guess you could. You could do all sorts of things. Let's go ahead and do it. So 2 pi times the orbital radius divided by an orbital period equals the square root of g times m over the orbital radius. We've got orbital radius a couple places. Let's see if we can collect those. So if I square both sides and move the orbital radius over, I get 4 pi squared over the period squared equals g m. Actually, if I square both sides, that r naught's going to be squared on the left. That's going to make this over r naught, and r orbit, cubed. Okay. And I'll do one more step just so that it looks the way that we typically see it. Typically, we move the period over to the other side. We move the gm and the r to the other side. So what you get when you do that is period squared is some collection of constants. It's 4 pi squared over g times m times the orbital radius cubed. This is a relationship that Johannes Kepler, which is a German astronomer, recognized, he didn't derive it, but he recognized it from loads and loads of data that Tycho Brahe took. Tycho was a Danish astronomer, scientist who took lots and lots of detailed measurements of objects in the sky. And again, Johannes Kepler analyzed a bunch of that data and got this. This is Kepler's third law. I'm not going to go through all of Kepler's laws. Take a astronomy course if you're really interested in that. They are very interesting. What the most interesting part to me is that he didn't derive them from first principles. He recognized them from data. Right? So he didn't know that this constant was 4 pi squared over gm because he didn't have g. Right? Isaac Newton hadn't come up with this idea of g yet. And Newton didn't know g either. Okay, so let's do one more example that uses this Kepler's third law. Again, we're relating orbital period to orbital radius, right? So a larger radius means a larger period. So to look back at the problem we just did, we said, I noted that the orbital period was like 7 hours and said, oh, then it must be closer than the moon, because the moon has a period of 30 days, right? More like 27, 26, depending on how you define it. So larger period must mean larger orbital radius. Okay, so yeah, let's do an example real quick. This is example number 16. Where are we? Here. So, Martian satellite Phobos travels in an approximately circular orbit of 9.4 times 10 to the 6 meters with a period of 7 hours and 39 minutes. Can we get the mass of Mars from this information? Oh, that's interesting. How else could we get the mass of Mars, right? We can't get the mass of Mars from Mars' orbit around the sun because the mass of Mars cancels out. Right? So we're going to have to get the mass of Mars from something that goes around it. And I think that's ultimately how we got the mass of the Earth, was looking at the moon. But we needed a good number for the distance to the moon first. And I think that was the limiting factor. Okay, so let's draw this. Let's see. So we have Phobos. That's way out here. What color is Phobos? Green. Sure, why not? And it's going around Mars. And Mars is clearly red. Sounds good. In a circular orbit. That's not a circle, but that's okay. And we know an orbital radius of 9.4 times 10 to the 6 meters, which is just a little bigger than the actual radius of the Earth, which gives you a sense of the scale of the size of Mars, right? Again, I didn't draw this to scale, but that's okay. And we're given an orbital period of 7 hours and 39 minutes. Let's convert that all to seconds, right? That's going to be much more useful. So 7 times 3,600. Oh, come on. Come on, please. Plus 39 times 60. What I get is 27,540 seconds. And I want to get the mass of Mars. So again, I've got a period and I've got an orbital radius. This is begging for Kepler's third law. Clearly, I just introduced it, so that's what we're going to talk about. But again, the crux of Kepler's third law is that period squared is proportional to orbital radius cubed. Right? That's what he noticed from this set of data for lots of orbiting things. And the proportionality constant is 4 pi squared. Again, not 4 pi quantity squared, but it's 4 times pi squared. It's 2 pi quantity squared. That's neither here nor there. G and the mass of the thing being orbited. In this case, that mass will be the mass of Mars. That's what we're solving for. So we can plug in. Just need a little space, but we can do it. So the period in seconds, again, we need all of these things to be in SI units for this to work out. 4 pi divided by 6.67 times 10 to the minus 11 times m. I overestimated just a little bit, but that's fine. 9.4 times 10 to the 6 cubed. So a little bit of careful algebra later, and what I get is the mass of Mars is 6.48 times 10 to the 23 kilograms. Oh, 23 kilograms, which tells me it's about an order of magnitude less massive than the Earth, which is kind of nice to have that number in your head, or a sense of the scale, right? How big Mars is compared to us. It's smaller. It's an order of magnitude smaller mass, and probably a smaller radius as well. Okay, yeah, this is good.